This is your presenter Asloop Mudassar, and I am presenting slide number 141th of the course on laser physics. Question is, describe an X-ray laser, problems related to X-ray lasers, and area of application. The answer is, in an ordinary laser system, atoms or molecules of laser medium are excited either through photopumping or through electron collision. This is done for an ordinary laser system. That is, there are two options, that we can excite the medium through photopumping, that is through the optical pumping, or through the electron collision. But in case of an X-ray laser, photopumping is not possible as it requires another X-ray laser or a strong flash lamp giving off X-rays. Collisional excitation is, however, theoretically possible. Inner electrons are excited to high energy states, and when these electrons return to their original positions, they make the atom to emit soft X-rays. In such a collisional excitation, the excited atoms become unstable. So this is an important point. In such a collisional excitation, the excited atoms become unstable due to the presence of the electrons in the outer shells of the atom, and thus lasing action cannot be achieved. So in the outermost shells, that is in the outer shells of an atom, you have already some electrons, and when you pump the inner electrons, excite the inner electrons to the higher outermost shells of the atom becomes unstable due to the presence of the electrons already occupying some orbits there. To overcome the instability of the atoms during inner electron excitation, the atoms are ionized by removing many electrons from the outer shells so that the vacancies in the outer shells are created for the inner electrons to occupy. The ionization is accomplished very quickly by heating the laser material, which here we can call it as a lasent, to high temperature using a laser beam to focus in line of a few centimeter in length and a fraction of a millimeter in thickness. So we can heat up the laser material using a laser beam in the form of a line focus. The length of the line focus could be a few centimeters, and the thickness of the beam is of the order of a few millimeters or a fraction of a millimeter. The scheme is what I would like to show you so that you can have an idea. The figure caption is X-ray beam production by focusing a high intensity line focused laser beam onto a plastic foil coated with a thin layer of yttrium. Lasing medium is created as a very hot, uniform cylindrical plasma. X-ray is produced from both ends of the line. So here you can see that this is actually a light gray plane is actually represents line focused laser beam, which is being focused over here at the yttrium foil, and it produces plasma over here, and due to that one the X-rays on both sides of this are emitted. The detailed description will be covered in the paragraphs or in the texts. So you should keep this geometry in your mind, that the beam from a laser source is line focused at the yttrium foil to heat it up. That is, the atom of the yttrium atom are heated to a very high temperature, and then of course what happens ultimately, we get the X-ray beams from both ends. The detail will be covered in the text. Okay, let me read this again very quickly. To overcome the instability of the atoms during the inner electron excitation, the atoms are ionized by removing many electrons from the outer shells so that vacancies in the outer shells are created for the inner electrons to occupy. The ionization is accomplished very quickly by heating the laser material lasent to high temperature using a laser beam to focus in line of a few centimeter in length and a fraction of a millimeter in thickness. And I have shown you the diagram through which you can understand the focusing of a laser beam in a dimension of a few centimeters, and the width of the beam is a fraction of a millimeter. This is used to heat up the laser material to a very high temperature. Now we want to talk about here in this paragraph we said that the most of the some electrons from the outermost shells are ionized so that we can remove the electrons and we can create the vacancies there. Vacancies in the outer shells are created for the inner electrons to occupy. So how this is created? The heating removes the desired number of electrons from an atom. For example, 29 electrons out of the 39 electrons from the yttrium are removed. The unbound ionized energetic electrons collide with the ions. So you see that when you ionize them, you have some unbound electrons available. The unbound ionized energetic electrons collide with the ions and thus collisionally pump or excite them to the desired level. The excited ions are de-excited by emitting X-rays. So you see that this process will remove the instability of the atoms, because when we have an ionized atom, then we can easily excite the inner electrons to the desired orbits, desired outermost shells. Lasing action occurs along the line of the plasma. So you can see over here the plasma is created over here when the laser beam is focused, and this is the material, the lasing material over here. So you can say the unbound ionized energetic electrons collide with the ions and thus collisionally pump or excite them to the desired level. The excited ions are de-excited by emitting X-rays. Lasing action occurs along the line of the plasma. Two X-ray beams are produced and travel in opposite directions as shown in the figure. Finding appropriate lasing materials, generating appropriate heating, desired obtaining or acquiring desired ionization states, and electron density and excitation to appropriate laser levels are the key challenges in the production of an X-ray beam. The system of an X-ray laser may be treated as that of a four-level laser system, as the lower laser level is almost empty. So the inner electrons are excited to the outermost shells, and when they come back to their original states, then of course the photons are emitted in the form of X-rays. The threshold pump power of a four-level system is given by. So this is the threshold pump power. P threshold is equal to gamma over eta P multiplied by h nu mp divided by tau and then multiplied by A over sigma, where nu mp is actually the minimum pump frequency. So where nu mp is the minimum pump frequency, or is actually the frequency difference between the upper laser level and the lower laser level. And A is which is equal to capital V over L, where capital V is the volume of the active medium, L is the length of the active medium. So capital A is actually the area of the active medium. The critical inversion is given by NC is equal to gamma over sigma L. So these formulas have been discussed while we discussed a 4-level laser system. So if you want to see the details of these mathematical equations, you are required to consult my slides on 4-level laser systems. So here the critical inversion is given by this formula, which is NC is equal to gamma over sigma into L. To find PM thermal, M stands for the minimum threshold. So PM threshold is the minimum threshold pump power. To obtain this quantity, you substitute sigma is equal to sigma P, where sigma P is the cross section at the transition peak. So this is the sigma P is actually the cross section at the transition peak in the gain profile. In the X-ray region, the upper lifetime tau is governed by the spontaneous lifetime tau SP. Because we are not involved in case of X-rays, there is no stimulated emission. So in the X-ray region, the upper state lifetime tau of the upper level is governed by the spontaneous lifetime denoted by tau SP. The following relationship can then be written as. So you see that here you can understand from this formula of the threshold pump power that you have tau and sigma in the denominator, and you can manipulate these two quantities in order to minimize the value of a P threshold. So that's why we are manipulating tau and sigma, and we are using sigma is equal to sigma P, where sigma P belongs to the cross section of the peak, and tau will be replaced by the tau spontaneous lifetime of the upper state. So the following relationship can be written: 1 over sigma P times tau SP, which is the spontaneous lifetime of the upper laser level, is this whole quantity, that is 1 over this quantity, is proportional to nu naught square divided by GT at 0, where GT is the total gain profile at the 0th frequency, that is at the central frequency. And here we have nu naught square is also represents the central frequency. So 1 over sigma P tau SP is proportional to nu naught square over GT evaluated at the 0 frequency, that is the central frequency. For homogeneous and inhomogeneous lines, we can write that GT at 0 is proportional to 1 over delta nu naught. And you can also have a complete profile of GT from one of my previous slides of this course. For homogeneous and inhomogeneous line, we can write that GT evaluated at 0 frequency at nu is equal to 0, that is the central frequency of the gain profile, will be proportional to 1 over delta nu naught, where delta nu naught is the transition line width, or is the line width of the gain profile. Thus, using h nu mp is equal to h nu naught, where nu naught is actually the central frequency of the gain profile, and we can substitute nu mp to be equal to nu naught, and we can write the previous formula in the following form, that is P, that is the pump power with minimum threshold value, that is P m thresh is equal to h nu naught over eta P, and then multiplied 1 over sigma P into tau SP, and then we have separated the term gamma times A. Now you see that from this equation, it follows that the PM threshold is proportional to nu naught cube, because this term in the bracket from the previous over here, you can see that this 1 over sigma P times tau SP is proportional to nu naught square. So nu naught square is coming from this term, and nu naught is already present with h nu naught. So we have PM threshold is proportional to nu naught cube. And then you see that here in this expression gt at a value of 0 is also present, which is proportional to 1 over delta nu naught. So if you substitute this value over here, you will find that pm threshold is proportional to nu naught cube and also proportional to delta nu naught. Where nu naught is lying in the soft X-ray region, because we are dealing with the X-ray region, so we then nu naught will be actually belong to the X-ray region. Where when the nu naught is lying in the soft X-ray region, and if the gaseous or the plasma pressure is moderate, then the line width is dominated by the Doppler broadening. So you see that under this condition that the pressure is adequate or moderate, that is the pressure is moderate, not high, then we can say that the Doppler broadening will be the dominant mechanism for the line width broadening. And under that condition, we can write that delta nu naught is proportional to nu naught, where nu naught is the central frequency of the regions of the X-rays which are emitted in our setup, and the delta nu naught is actually the width of the line width of the in terms of frequency. So we can see that delta nu naught will be proportional to nu naught under the condition that the Doppler broadening is the dominant process. Under such a condition, we can write this equation by substituting the value of delta nu naught to be proportional to nu naught, and we can say that the minimum threshold pump power will be proportional to nu naught to the power 4. In X-ray region, the upper state lifetime becomes very short, of the order of a femtosecond, and the line width is dominated by the natural broadening. And under such a transition, under such a condition, we can write that delta nu naught is proportional to 1 over tau sp. And this tau sp is also inversely proportional to the cube of the frequency. So we can write delta nu naught is proportional to 1 over tau sp is proportional to nu naught to the power 3. So if you substitute this value of delta nu naught over here, then you can have the minimum pump threshold power will be proportional to nu naught to the power 6. So minimum threshold pump power will be proportional to nu naught to the power 6. That is PM thresh in the X-ray region is 3 orders of magnitude greater than its value in the visible region. So you see that for the visible region, this PM threshold will be proportional to nu to the power 3. But for the X-ray region, this PM threshold will be proportional to nu to the power 6. So that's why we have said that PM threshold in the X-ray region is 3 orders of magnitude greater than its value in the visible region. And what is its effect on the wavelength? The wavelength reduction in the soft X-ray region is by a factor of 50 of the visible region. For example, if in the visible region you have lambda is equal to 500 nanometer, then for the soft X-ray region, this wavelength will be reduced to 50 times. So we have lambda of the order of 10 nanometer. So in the soft X-ray region, you have wavelengths in this region around 10 nanometer, and in the visible, you have the wavelengths in the region around 500 nanometer. So from here you follows that the wavelength is reduced by a factor of 50 for the soft X-ray region, whereas the minimum threshold pump power is increased by 3 orders of magnitude. So in order to produce the pumping mechanism in case of soft X-rays, you need to have the pump power much 3 orders of magnitude greater than the pump power required to produce the lasing action in the visible region. Due to enormous power, the dielectric mirrors for proper reflectivity requires multi-layer coatings. So you see that here there is a question of multi-layer coatings. In order for the mirrors to stand this high power, the number of multi-layers could be as high as 100 for the required reflectivity. Scattering of light could occur at multiple interfaces. So you see that due to the multiple coatings, multiple interfaces are present. So if you have 100 coatings on the mirrors, then it means that you have 100 multiple interfaces, making such a mirrors as quite lossy. So the mirror becomes quite lossy because at each interface you have a loss due to the scattering of the light and due to the change in the refractive indices of the consecutive interfaces. The mirrors cannot withstand high intensity X-rays beams for a long time. So this is a question, for the production. One of the problems that the mirrors cannot stand for a long time the X-ray intensity of the X-ray beams. X-rays are therefore operated as ASE, that is amplified spontaneous emission device. And you know that I have also discussed amplified spontaneous emission in one of my previous slides. So you are referred to consult one of my previous slides on this course to see the details about ASE, which is amplified spontaneous emission. So the X-rays are therefore operated as ASE devices. That is, we don't use the mirrors. Due to large number of coating layers, the difference in the refractive indices between the consecutive layers become very small, and finding the appropriate materials become very difficult. So for example, in a typical case, if you are using 100 layers, 100 multi-layers coatings, then of course it means that you need to have different materials with varying refractive indices very close to each other between the consecutive interfaces, and thus there is a great problem of finding appropriate materials for such coatings. Let us consider an example of the X-ray recombination laser. X-ray recombination laser using selenium ionized to have charge 24 plus. So Se24 plus as the active medium, where the selenium atom is 24 times ionized. The laser medium consists of multi-ionized species. So you see that then this selenium, which is ionized by 24 times, will act as a active medium for the laser to be obtained as X-ray recombination lasers, which will be discussed now. The laser medium consists of multi-ionized species. Se24 plus is excited using second harmonics of 532 nanometer generated by a Novet laser, which has a pulse energy in kilojoule range and a pulse duration in nanoseconds. The beam is line focused with a line width equal to L is equal to 1.2 centimeter, and the beam width is of the order of 200 micrometer on a thin foil of the order of 75 nanometer thick of selenium using an arrangement shown in figure number 1. The foil explodes and a thin line of cylindrical plasmas is generated. Ion electrons recombination process leaves the plasma with Se24 plus, that is the selenium ionized by 24 times. So you see that this tells you the description, paragraph tells you the description that how selenium can be ionized by 24 times to obtain Se24 plus. The electronic configuration of Se24 plus in the ground state is, that is, we are considering the electronic ground state, that is the electronic configuration of Se24 plus is 1s2, 2s2, 2p6, which is also the electronic configuration of the neon atom. But here you see that we are considering the ion of the selenium. During the collisional excitation of this ion with the electrons of the hot plasma, Se24 plus is excited to the states 2p5, 3p, 2p5, 3p, and 2p5, 3s. That is, one of the p electrons from the 2p6 will move to the next 3p orbit, or the one of the p electrons from the 2p6 will move to the 3s orbit. So these are the two levels to which the Se24 plus can be excited. That is, it can be excited to 2p5 3p and 2p5 3s. The transition from 2p5 3s to the ground state of the selenium 24 plus is short-lived, and the transition from 2p5 3p to 2p5 3s gives two lasing wavelengths, 20.63 nanometer and 20.96 nanometer. 20.63 nanometer and 20.96 nanometer. These two wavelengths are emitted when the transition from 2p5 3p to 2p5 3s occurs. Due to highly ionized selenium, these transitions involve inner electrons, and thus the emission falls in the soft X-ray region. Laser beam exits from both ends of the plasma line with a single pass gain of the order of G equal to e to the power sigma p times n times L of about 700. This gain profile has also been discussed in one of the previous slides. Different lasing materials have been investigated, including neon-like ions, which is Ag37 plus to argon 8 plus, hydrogen-like ions, aluminium 12 plus to carbon 5 plus, lithium-like ions, silicon 11 plus to aluminium 10 plus, nickel-like ions, Au51 plus to Eu35 plus. The obtainable wavelength range from these materials is 3.6 to 47 nanometer, and the single pass gain varies from 10 to 1000. Possible application areas apart from high density plasma diagnostics include X-ray holography, X-ray microscopy, 3D imaging of sub-nanoparticles, imaging in biosciences, and X-ray lithography, etc. So you see that here in this lecture, I have discussed very briefly useful information about the X-ray lasers, the difficulties, and especially I have discussed the selenium, how we can produce a selenium ion and how we can obtain the laser beam from such a lasers. And we have also compared with some data with the visible range. I hope that the information will be useful. So this is the end of slide number 141.